Hey guys, Justin here, and welcome to our 13th example video following our course on abstract algebra. Now, today's examples are going to be all on external and internal direct products, so with my introduction out of the way, let's go ahead and get into our first example here. So for our first example, we want to prove that d sub 4n is not isomorphic to d sub 2n cross z2. If you recall, we have a result in the lecture video corresponding to this example video that d sub 2n is isomorphic to d sub n cross z2 as long as we have n is an odd number. And you can see we do not have that case here as we have a 2n instead of n, so 2n is obviously not an odd number here. So to disprove this in general, I'm just going to provide a simple counterexample. So we are going to go ahead and consider d4, and of course d4 is of the form d sub 4n. And so what we want to do is we want to show that d4 is not isomorphic to d2 cross z2. So in order to prove they're not isomorphic, let me go ahead and list out the elements of both of those here. So let's start with d4. So d4 is the group corresponding to the symmetries of a square. So we have the identity, r squared, and r cubed, where each rotation is a rotation by 90 degrees. Then we have a reflection s, then we have sr squared, and sr cubed. Great. So if we did that right, we should have 8 elements, and we in fact have 8 elements. So now let's go ahead and list out what the elements of d2 and z2 are, and then we can get into where we run into a problem. So d2 is just going to be equal to the following. We will have e, r, s, and sr. And of course, our z2 is simply going to be equal to the set 0 and 1. Great. So I want to go ahead and note that in order for us to have an isomorphism, we must preserve commutivity. So I want you to note that the only elements that commute in d4 are our identity element and r2 due to the commutation relation, where if we move our r squared to the right, we will have r to the 4 minus second power, which is still r squared, so it will in fact commute. Whereas here in d2, all of these elements commute, as only d1 and d2 are the abelian groups in dn. Great. So you can see right away we have a problem with that, as like I said, commutivity must be preserved in an isomorphism, and here we only have 2 elements in the center of d4, and we have 4 elements in the center of d2, so they cannot be isomorphic. Great. So with that out of the way, let's go ahead and get into our next example. So for this one, we want to write z3 cross z6 cross z10 in as many different forms as possible. So I want you to recall the following result from the lecture video, and that is that we can combine a zn cross zm into a z sub nm if and only if we have that the GCD of m and n is equal to 1. That is to say that they are relatively prime. So basically what we're going to do is write as many combinations of this as possible by combining different relatively prime elements of z3 cross z6 cross z10. So let's go ahead and write out the first one, which may be the most obvious one, and that is just to break this down into a bunch of primes. So that'll be z3 cross z3 cross z2 by breaking that z6 into z3 cross z2, which we can do by the relationship I wrote above there. And that will be cross z2 and cross z5. Great. So from here, I want to note the different numbers that we can combine. We can combine 3 and 2, 2 and 5, and 3 and 5, as well as 3 and 10 potentially. But we can't combine 3 and 3 or 2 and 2 because they are obviously not relatively prime. So let's go ahead and work on some combinations. Well, for one, what we just wrote out is a possible form. So let's go ahead and write out another one. Let's see, we can combine our 3 and our 5 to get we can combine a z3 and our z5 to get a z15. So let's go ahead and do that. So what we'll be left with is z3 cross 2 copies of z2, and then we will have that will be cross z15. Great. And so from here, we can actually combine our z2 and our z15, as 2 is relatively prime to 15, and that will give us z3 cross z2, and that will be cross z30. Great. And so you can see that we could write out another one where we combine our z3 and our z2, and that will give us z6 cross z30. Great. So now let's see if we can come up with another one. Well, we could just write out this one where we combine our z2 and z5 and maintain our z6 being broken up like that. So that'll give us z3 cross z3 cross z2 and then cross z10. And similarly, we can do the same thing, but combine these two elements here into z6 and leave our z10 broken up. And that will give us z3 cross z6 cross z2 and then cross z5. So this one we've just written out lends itself well to another one where we can write this as z6 cross z6 and that will be cross z5. And I think you get the idea here. This is the method we would use to generate the rest of them. I'm not sure if this is all of them, but I don't think it would be too hard to find the rest of them if I missed any. So if I missed any, make sure to post about it in the comments. And let's go ahead and get into our next example. So for this one, we want to prove that the subgroup, which is defined as the set generated by 2 to the m times 3 to the m. That looks like that's a typo. It should be at 2 to the m times 3 to the n. So let me go ahead and clarify that here. And that will be as m and n range across all integers, which is a subgroup of the rational numbers with multiplication, is an internal direct product isomorphic to the integers cross the integers. Great. So let's go ahead and start this problem by proving that it is an internal direct product, and then we can show that it's isomorphic to the integers across the integers. So if you recall, the things we want to prove that something is an internal direct product are that it is the product of two subgroups and that the intersection of those two subgroups is equal to just the identity element. So that gives us two things to show here. So let's go ahead and define our subgroups in the following way. Let's let our subgroup H equal the following, where we have 2 to the m, such that m ranges across all integers. And let's also let our second subgroup be equal to k, where we have 3 to the n as n goes throughout all integers. So obviously by construction, h times k is going to equal our entire group here. Let's go ahead and just refer to this subgroup here as S. So I'll go ahead and write that. So obviously we have that S is equal to H times K. So that means that all we need to show is that H intersect K is equal to just the identity element, which in this case will be just 1. Great. So let's consider two cases then. So case 1 is that we have m is equal to n, which is equal to 0. And that will give us the following. We will have 2 to the 0 is equal to 3 to the 0, which is equal to just 1. So that means we will obviously have that 1 is in the intersection of H intersect K. And so case 2 will be all other possibilities here. So if case 2, otherwise we would have the following, and that is 2 to the m is equal to 3 to the n. And obviously that this is not possible, as we have a left-hand side which is even and a right-hand side which is odd, and no matter what you plug in for the exponents there, we will not be able to have an equivalence there. So thus we have proved that we have the identity and the intersection and that all other cases are impossible, so this is an internal direct product. So now all we need to do is show that it is isomorphic to the integers cross the integers, and we're going to do that by describing a bijection between the two. So let's go ahead and do that now. And we're going to do that with the following map, which I think is probably the obvious map here. So we're going to take phi, which goes from the integers cross the integers, and it goes into our subgroup, which we defined to be S. And what phi is going to do is it's going to take an m and an n from the integers, and it's going to map them in the following way, where we have 2 to the m times 3 to the n. Like I said, probably the fairly obvious function that you would come up with. And from here, now we have to show a few things to show that this is a bijection. But first, let's go ahead and make sure that this thing is well defined. So let's suppose we have the following, and that is that m and n is equal to x and y. Great. Well, then phi of mn will be equal to the following. It'll be equal to 2 to the m times 3 to the n. But since we know that m is equal to x and n is equal to y, that will simply be equal to 2 to the x times 3 to the y, but that is the exact definition of phi of x, y. So that means our function here is well defined. Great. So next we're going to prove that this is operation preserving. And so for that we are going to consider the following. We are going to consider phi of mn plus xy. Great. Well, breaking that down will give us phi of m plus x, comma, n plus y. And now we can use our definition of phi here. So that would give us 2 to the m plus x times 3 to the n plus y. Great. And using the definition of exponents, we can rewrite that in the following way, where we have 2 to the m times 2 to the x times 3 to the n times 3 to the y. And now we can use the commutativity of just regular multiplication to write that in the following way, where we have 2 to the m times 3 to the n times 2 to the x times 3 to the y, which is of course equal to phi of mn times phi of xy, which is all we needed to prove to show that this preserves the operation. If you look at the extreme left and right-hand sides here. Great. So now all we need to do is show this is a bijection by proving that it is both injective and surjective. So let's start by proving injectivity in the following way. So for this one, we are going to suppose that we have phi of mn is equal to phi of xy. And then we want to show that that means that mn is equal to xy. But this is pretty straightforward, and I would say almost obvious, because once we apply phi to m and n, we will get that 2 to the m times 3 to the n is equal to 2 to the x times 3 to the y. And that very obviously implies that m is equal to x and n is equal to y, which is all we needed to show that mn is equal to xy. Great. Now for surjectivity, this is super obvious as it is given by our construction of our function here. So I'll just go ahead and write that this is by construction, as there is not going to be any element from our codomain that cannot be mapped onto by our domain, given that they are both pulling from the integers there. Great. So that proves that we have constructed a bijection between them, which proves what we wanted to prove, and that is that this is isomorphic to the integers cross the integers, which finishes this problem off. So let's go ahead and get into our next example. So for this one, we are going to let m and n be integers, and we want to prove that the set generated by m and n is equal to the set generated by d if and only if d is equal to the GCD of m and n. Great. So because we have a set equality here, we're going to prove this by double inclusion. So let's go ahead and start by proving the forward direction here first. So let's go ahead and suppose that we have some element, let's call it little a, which is in the set generated by m and n. Well, by definition, that means that we can write a in the following way, where a is equal to m times something, let's just call it s, plus n times something, let's call it t, and this will be with s and t being integers. Great. And then we have that d is equal to the GCD of our m and our n there. And this means that d will divide m and d will divide n, which means obviously by the way a is written here that d must divide a. But if d divides a, that means we can write a as a multiple of d and some other number, which is the exact definition of what it means to be in the set generated by d. So that means that a is in that set there, which proves our forward direction. We have that our set generated by m and n is a subset of our set generated by the GCD of m and n. Great. So now let's go ahead and get into the reverse proof here. And we're going to do that by supposing that we have some element a in the set generated by the d, where d is equal to the GCD of our m and our n here. Great. So now we're just going to use the definition of the GCD here. So that means that we can write d in the following way, where d is equal to m times s, and then we'll do plus n times t, with our s and t being integers here. But because a is in the set generated by d, we also have that a can be written as d times some other integer. Let's just call it b. And like I said, b is an integer there. So now we can make the following substitution, where we have that a is equal to ms times b plus nt times b, and that is obviously an element of the set generated by m and n, which means we have proved that the set generated by D is a subset of the set generated by M and N. And because we've proven both directions, that means that we have that the set generated by M and N must be equal to the set generated by D. Great, so that finishes this one off. So let's go ahead and get into our second to last example. So for this one, we want to let M and N be integers, and we were going to prove that the set generated by M intersect the set generated by N is equal to the set generated by L if and only if L is equal to the LCM of M and N. So just like the last one, we are going to be proving set equality by double inclusion here. So let's start by doing the forward direction, which is to show that the intersection of the sets generated by M and N is a subset of the set generated by L, which is the LCM of M and N. So just to simplify some notation here, let's go ahead and let this intersection here be equal to the letter capital A, and we can go ahead and let the set generated by the LCM of M and N be equal to B. That way I don't have to write those out so many times. So now we're going to go ahead and suppose that X is in A. Well, by the definition of the intersection, that means that X is in the set generated by M, and also that X is in the set generated by N. But that means that X is a common multiple of M and N. And so then we can use the division algorithm here. So I'll go ahead and write that. By the division algorithm, which I will abbreviate DA, we can write X in the following way, where X is equal to Q times L, where L is the LCM as stated in the problem. And we have plus some R with the following inequality, where R is greater than or equal to 0, which is strictly less than Q here. Great, but we can rearrange this equality in the following way, where we have that R is equal to X minus Q times L. And now in order to finish this off, we want to show that X must be equal to Q times L, which will show that it is a multiple of L, and thus in the set generated by our LCM L. And in order to do that, we need to show that R is equal to 0. But R must be equal to 0, because if R is not equal to 0, then it is a common multiple of M and N, which is less than L, which is of course not possible because L is defined to be the LCM of M and N. So I'll go ahead and write that. R is equal to 0, but that means that X is equal to Q times L, and that will finish off this forward inclusion. As we have X is equal to Q times L, that must mean that X is in the set generated by the LCM L there. Great. And now the reverse direction is pretty easy. So let's go ahead and do that now. So let's suppose that we have X is in the set generated by the LCM L. Well, by definition of the LCM L, that means that X is a common multiple of M and N. So I'll go ahead and write that. X is a common multiple of M and N. But as we outlined in the forward proof, that is the same thing as being in the intersection of the set generated by M and N. So that finishes this one off. That means that X is in the intersection of M and N. Great, or the sets generated by M and N. So because we've done this forward and reverse inclusion, we have proved that these two sets here are equal. So we have finished our proof off. So now let's go ahead and get into our last example. So for this last problem, we want to express U165 as an internal direct product of subgroups in 4 different ways. So before we get into expressing it these different ways, let's go ahead and look at the factorization of 165. So 165 is most obviously divisible by 5, and when we divide it by 5, we will get that it is equal to 5 times 33, but that's of course equal to 5 times 3 times 11. And we're going to use this factorization to our advantage when we write this out in 4 different ways. But first I want to remind you the requirements that we need to meet in order for this to be an internal direct product. I know I went over them earlier in the video, but let's just go over them at least verbally one more time. And that is that we can write U65 as the product of 2 subgroups, and those 2 subgroups must intersect to just the identity. And so we can use this along with the some results that we've done with external and internal products to write this out as an internal product of subgroups in 4 different ways. So let's go ahead and start by writing the first one. And I'll do this by defining our subgroups. So for this first one, we'll let our first subgroup N1 be equal to the set generated by the number 5. And we will let our N2 be equal to the set generated by 33. Great. And so then we will have that U165 is isomorphic to N1 cross N2, or the set generated by 5 cross the set generated by 33. And for the rest of these, we are going to be using the factorization in just this way to write out an isomorphism for U165. So let's go ahead and do another one. So for this one, let's go ahead and write N1 as the set generated by 3, and then we can write N2 in the following way, where it is equal to the set generated by 55. And just like before, U165 is isomorphic to N1 cross N2, which in this case is equal to the set generated by 3 cross the set generated by 55. Great. So now we only have 2 more to go here. So let's go ahead and do our third one, and that will be N1 is equal to 15, or the set generated by 15, and we'll have that N2 is equal to the set generated by 11, and we will have that U165 is isomorphic to N1 cross N2, or in this case, the set generated by 15 cross the set generated by 11. Great. And so for our fourth and final way to express this as an internal product of subgroups, we will have 3 subgroups here. We will have N1, that will be equal to 3. We'll have N2, which is equal to 5. And lastly, we will have N3, which is equal to 11. Great. And so then we'll see that U165 is equal to N1 cross N2 cross N3. Or in this case, it'll be the set generated by 3 cross the set generated by 5 cross the set generated by 11. Great. And you can count them and see that we have written this in 4 different ways as the internal direct product of subgroups. So that finishes this last problem off, and that's a good place to stop.